So last time we discussed a cycle. What cycle was it? What was it called?
Carnot.
Carnot cycle. What was special about the Carnot cycle? Most efficient cycle possible, yeah. What's that? Reversible, yeah. Okay, so we had the Carnot cycle. It's reversible. Yeah. And what does that mean? When you say something's reversible, what goes into that assumption?
Of energy put in energy. The piston thing you did.
The piston thing I did. All right. Yeah, so that had to do with small changes. Small, teeny tiny changes. Okay? So you're going to have to, if you make large kind of discrete shifts on, off, that kind of thing, then then it becomes irreversible. You have to supply extra work to get it back to where it started. Okay? Also, no friction, none of that kind of stuff. Okay, so this is clearly an idealization. It's not a real thing, but it's good to have such a thing in the back of your mind. Okay, what was the formula for the Carnot efficiency? Tc over Th. And if you can't remember which, just remember it's got to be less than 1. And the hot temperature is more than the cold one. So it's got to be that. Now, these temperatures were not just, what kind of temperatures did they need to be? Absolute temperatures. Rankine or Kelvin. If you use Fahrenheit, it won't, you can get minus signs off and stuff like that. So these must be absolute temperatures. In fact, I'm not going to do it because we're running short in the semester and all that. You can actually imagine that you had a Carnot cycle and then ignore the fact that we had ideal gases. Okay, just set that aside. And what you can do is you could actually use Carnot cycles to define an absolute temperature scale, and it really would have nothing to do with ideal gases, whatever. And it just would happen that the scale that you would get using Carnot cycles would be, well, that would be an absolute temperature scale, and one such example would be what we get by thinking about ideal gases. Both methods would lead to absolute zero in the same sense and all that, so they align. But in fact, this is the original, I believe this was the original way that I think it was Kelvin suggested to define an absolute temperature scale. Okay, so that was true. The important way I wrote it, though, this is fine for efficiencies, but mostly I don't really care about that. Instead, I want to think about heats. Okay, so what was the key point in terms, like rephrase this in terms of heat? The ratio of the heats is what? So if I write down the key point, was it Q C over QH equal what? TC or TH. So the ratio, people will say ratio of heats is ratio of absolute temperatures. Okay, that's kind of the key, the punchline, the summary statement. And that was true for reversible cycles. All right. Now, one careful thing here. These are absolute value numbers. These heats are positive quantities. And so really, QC in that example was negative. So you just got to watch when you go to do the math. Okay? All right. Lost my. All right. Okay, so what we're going to do is I'm going to make a couple statements. We're going to go from here. We're going to talk about the second law of thermodynamics. Second law of thermodynamics. We're going to state this in a few different ways. And we will show that they are equivalent. Okay? They don't sound the same at all. It's only when you kind of get into the details to see that they are equal. The one. All right, let's start with this one. Right? I'm going to start with the Clausius statement of the second law. We're going to have three different ways to say it. Okay. Oh, just a quick aside. Go back to whenever you had to do logic in math class or whatever, right? If A implies B, what's the contrapositive of that? A implies B, then what's the contrapositive? A implies B, or not B implies not A, right? So with some of these kind of thermodynamics arguments, a lot of times it's easier not to prove the direct statement, but instead to prove the contrapositive. Okay, so all right, so that's so remember. So like, if I say that all dogs have 4 legs, so then if it's a dog, it has 4 legs. Okay, let's just assume that that's true. That statement, mathematically, you could say is if it doesn't have 4 legs, it's not a dog. Okay, those are equivalent statements. Right? It doesn't mean that the first statement is true or false. It's really just logically those are equivalent. All right. Okay. So the second law of thermodynamics. So the Clausius statement. Clausius did a whole bunch. He had several ways to say this, I believe. So I'm just picking one, but it gives you kind of a flavor of it. So what we're going to do in this case is we're going to kind of do this diagrammatically, and we're going to have heat and work kind of is going to follow the direction of arrows. So I'm going to use a rectangle for a reservoir and a circle for a cycle. Okay. All right. So here's the Clausius statement. All right. It is impossible for a cycle to run in such a way that the only, underline only, effect is to extract heat from a cold reservoir and deposit it in a hot reservoir. What does that mean? Break that down. So let's think about a refrigerator. Think about a refrigerator. What does a refrigerator do? Cools objects. Okay, so you have an object that you want to be the food. Okay, is that the cycle, or is that a reservoir?
Reservoir.
It's a reservoir. It's cold, and we want to move heat from the food. Where's the cycle in all this? Well, it's the thing inside your refrigerator, right? You got refrigerant, you got a compressor, you got an evaporator, you got like a throttling valve, you got all sorts of stuff inside there, right? That's all that runs. That part is the cycle. And what does it do? What does your refrigerator do? There's a coil, right? In the back of the fridge, you got that coil to exchange heat that goes into the kitchen, right? So here's the deal. The kitchen is warmer than the food, hopefully, right? So I'm going to do this where I put the warm thing on top. So I've got a reservoir here. I'm just going to put H for hot. It's going to be at a temperature TH, whatever, TH for hot. And I'm going to have another reservoir. So that's the kitchen. Okay. And down here, I have a cold reservoir at temperature TC. And a reservoir is just a big object who I imagine, in this case, I can imagine it's giant. The temperature doesn't change at all, right? But if you don't like that, you can let it be big but have a small mass and whatever, jazz it up if you want. Right? And operating in the middle between the food and the kitchen is the refrigeration cycle with the refrigerant or whatever. Okay? So I'm going to put this with a circle for my cycle. And what happens? It's in contact, right? So what does your refrigeration cycle do? Do? How does it interact with the food?
Extract the heat from it.
Extracts heat from it. So it's going to draw, you're going to have heat from the food or into the cycle. Okay, because there's always an issue with minus signs and perspective. Heat that the cycle gains, the reservoir must lose. Right? So you got to just be clear on your perspective, pluses and minuses. Okay? What else? What about with the kitchen?
Dissipating the heat.
Right? So that means you get heat deposited into the reservoir. Anything else happen in your refrigerator?
Work.
Work, yeah. What do you have to do to start your fridge? Plug it in. Okay, so is that going to be work going into the fridge or out of the fridge? Into, yeah, you apply it. Right, so we're going to have work going in. This is a refrigerator. This is what happens in your kitchen.
Would a fridge be more efficient if the heating coil is like directly in contact with the outside air conditioner?
Presumably, if you have better heat exchange, yeah, you can do things. But that's not the point. Let's not get derailed. Let's focus on the second law of thermodynamics. Okay, now that's a real thing. This is a real refrigerator you can have. Let me go ahead, just for fun, let's imagine something like this. Let's just have another, this is a fridge, and this is going to be an engine. These are real devices, while we're at it. So you're going to heat in from the combustion, or whatever. You're going to send heat into the air in the form of exhaust, and it produces work. Okay, so these are real devices. These are the things which we see in our everyday life. Now, should have started with those. Okay, now let's go back to the Clausius statement. What does Clausius say?
It's impossible for them to just extract out one of the other.
So what is he saying? Draw the thing that he says can't happen. What does he say can't happen?
From cold to from cold reservoir to heat reservoir.
Yeah. Well, that's what this does.
So you're just saying,
Because maybe it just implies that there must be some work involved.
Ah. So what is the thing that he said? A refrigerator moves heat from cold to hot. Okay? We know that happens. The key thing about Clausius is he says such that the only effect is to extract. So the thing he's saying is you can't have this. He's saying if you don't plug the fridge in, your food's not going to get chilled. Okay? You have to plug your refrigerator in. There's no magic refrigerator.
So it's not a free energy system.
So I'm going to call this the Santa Clausius statement. No magic. Sorry, I don't want to. Sorry, guys. Santa Claus isn't real. Okay, I'm just trying to make the connection that hopefully we all know that. But you know, sometimes if I just assume, then people get. And this, right? Gabe, going back. Don't ask the why question. Why am I connecting it? Right? Not real. Not real. Okay. All right. No magic refrigerator. Okay. There's no magic fridge. Okay. Is this? Let's imagine you had such a thing. Okay. Got my magic wand. Zing, got one. Okay. Does that break the first law of thermodynamics? Does it break energy conservation? What's delta U for the cycle? Cycle. What's delta U for the cycle?
0.
0. There's no work. So what's the work? 0. So what does the first law tell me?
No work cycle is equal to the internal energy cycle. So if there's no internal energy, there's no work, it's not equal.
So that means, no. If there's no work, all it says is the total heat has to be 0. Right? So as long as you balance Q in and Q out, it's fine. This doesn't break. A magic refrigerator doesn't break the first law of thermodynamics. Energy in, there's no work. As long as the heat in is the heat out, it's okay.
If there's no work input, there'd be no way to stop the cycle, they can run away cycle.
Well, cycles by definition go forever. Yeah, that's the. I mean, you can run it for as long as you want. So we know that there is no such thing as a magic refrigerator, right? Right? Okay. There's no magic refrigerator, but the first law of thermodynamics doesn't tell us anything about that. So we need some other. It's like in geometry where you need several different axioms to prove the different relationships. One isn't enough. Well, first law wasn't enough. So it must be that we need some other axiom. Because somehow, so I'll write it out here. Here's the statement. Somehow, this never happens. Okay? Somehow it never happens. And the first law doesn't explain that, so there has to be some other thing which proves that. He makes it into a statement. He's going to postulate that cannot happen. There's no magic refrigerator. To have a refrigerator, you've got to plug it in. Okay?
could you do something with the engine there so that the heat out of the fridge goes into the engine and then
We're going to play games like that in a minute. right? Hang on to that thought. Okay? Hang on to that thought. All right, that's the Santa Clausius one. No magic refrigerator. Santa Claus lives where it's cold. Refrigerator, cold, magic, bad. Got it? No, I mean, I remember as a student, I'm only going to give you two. This is I'm going to call this one of the wordy ways to say the second law. It's a lot of words, like an English sort of thing. And I think we had like 4 different ones. And at some point I remember like, Jesus Christ, I can't think of it. I mean, Clausius had like 3 of them. It's like, I couldn't remember who said what. So I'm trying to help you guys have a way to remember who said what. And I'm only going to give you 2 just to give you a flavor of them. The others, like all the things, all the arguments are just like variations on a theme. It's basically the same, you just change the detail a little bit. Okay, that was statement number 1. Statement number 2 is going to be the Kelvin Plonk statement. Version. And again, I think these guys had multiple different versions. So, you know, from like 1850 to 1900, even a little after that, 1905 or so, there were like different people were trying to come up with what was the best way to write the second law of thermodynamics, and there are different versions, and then it was like a game to prove that, oh, they're all actually equal. So if you had one, if you assumed one, you could derive the others, and backward, you could prove it both ways, so they're equal. So anyways, this is another one. This one, so the first one says no magic refrigerator. This one says no magic battery. I don't know what else to call it, so that's what I'm going to call it. Okay, there's no magic battery. What would you do if you had a magic battery? You just like hold this object. What would you do? Well, I would use it, right? I would use it to power my computer, power Zach's cell phone, right? Remember what I said, Zach? Would never be able to do? You never be able to hold the end of that plug up and just suck the energy in and charge your phone. Can't happen. That's no magic battery. Okay? So the statement is statement is it is impossible for a cycle to operate such that its only effect is to extract heat from a reservoir and produce work. Okay. Let's compare this to these devices are real. This happens. These, you know, this is a refrigerator, that's a car engine, okay, or that, whatever. These happen. These are good. We know these exist. Compare this one, because we're talking about producing work. So now we're talking, think about a power cycle. Okay, so think about a power cycle. Why is it? So that, there you go. You got heat, you got it's producing work. Well, why doesn't it break the second law, the Kelvin Plonk second law?
It's not extracting.
Extracting means pulls out. So that pulls heat out of the reservoir. What else does that do? Does that only pull heat out of the hot reservoir? What else does it do? Well, that's what I said.
Does it pull outside the outside of the?
This one extracts heat. So this says that the magic battery would extract heat and produce work. That one extracts heat from the hot reservoir, pulls it into the cycle, and produces work.
Has to send heat to a cold room.
There you go. There's always exhaust. Yeah, you always have heat dumped into the cold reservoir in any power cycle. Okay, so what this says is the following. This there's only one reservoir in the Kelvin Plonk statement, so it doesn't. There's no point in saying hot or cold. It's just whatever. Okay. The Kelvin Plonk no magic battery statement says this can never happen.
Is that kind of just saying if you're burning something, you're not going to get like probably smoke or something that would be coming to the cold thing?
Well, these are cycles, so that's not a cycle. That's more associated with the third statement, which is the entropy statement. These are equal to statements about entropy not decreasing in things, but they sure don't sound like it because you don't see it in it. Okay, but they're equal to that. If you have these, you can prove that, and if you have that, you can prove these. Go back and forth, they're equal. Okay. No magic refrigerator, no magic battery. What I want you guys to do, let's do table, and you three work together. We're gonna do some math proofs. Everybody's so happy about that. No, these are the best proofs ever. They're graphical in nature, right? They're graphical in nature. So what I want you to do is we're going to prove, here's what we want to prove. In math class, if you have A and B, if you can prove A implies B and B implies A, then you declare that they are equal statements. Right, so you can prove forwards and backwards, then they're the same. Yeah? So what I want you to do, here's the way the game is played. Okay, hold on. What we want to do is prove that no magic refrigerator is equal to no magic battery, and no magic battery is equal to no magic refrigerator. That's actually really hard. Well, not really hard, but anyway, what you're really going to do is prove the contrapositives. Prove that if you had a magic refrigerator, you could construct a magic battery, and prove that if you had a magic battery, you could construct a magic refrigerator. All right? So I want you to take a second, and I'm going to, I know, I'll hand out pieces of paper. You guys will work at your table. Think about how you could do that. So, first one, I would suggest. So what we're going to do is, step one, prove, what we want to prove is that Clausius implies Kelvin Plonk. what you're actually going to prove in reality is that the opposite of Kelvin Plonk implies the opposite of Clausius. So what I want you to do is assume that you are allowed to have a magic battery and use that to show that you could then produce a magic refrigerator. Let's do that one first. And then we're going to prove it the other way afterwards. Okay? So take a second. Do that. I'm going to hand out some paper.
And just rip off there.
Well, I've got a big pad there. All right. All right. All right, you three in the back, get together. Brainstorm. Okay. I'll also give you a hint. If you can balance, let's say you have just a hint. If you have a reservoir like this, and you just have equal amounts of heat, so you say Q in, and you have Q out. Oh, okay. If you can balance Q in equals to Q out, that's just the same. That's just the same as just taking a hose and just connecting them like that and just ignoring the reservoir in the first place. Right? If I have a heat, like a heat in and heat out, like two pipes, one with hot water in and one with hot water out, if the amounts of heat are exactly the same, you could just bypass wherever they went and just like couple them back together. So, all right, so this is the same as just disconnecting a reservoir, just so you know. Okay. How could you do that? How could you do that? So I'll give you guys 3 minutes here to think about it, and I'm going to give you a suggestion. Sorry.
Why is there heat coming out of the air, like the top part, the battery, just like heat already stored on battery?
Well, it's not really a battery. I'm just trying to come up with a pithy way to say it so that you remember. Right? What it really says is this. It's not really a battery. But it's a device that produces work. So if you could have a magic battery, if you could power a normal refrigerator and use it to come up with a big device whose overall effect is to move heat from cold to hot. Can't happen in real life, but if you have a magic battery, you can make it happen. Therefore, all right, the magic battery. So that's how it would go. The thing I'm not really having you chase through too much are the numbers. What you have to do is make sure that the work needed by the refrigerator is the work produced by the battery. And using the first law, then that number has to equal the work, the heat extracted from the kitchen. And basically what you can show is that this heat is always bigger than this heat. So the net amount of heat goes into the kitchen. I'm not having you chase through those details, but it does work out that way. Just when you use the first law in combination with this. All right. Everybody see how they can do that? Okay. That's proving it. So that means we've shown this. That means we've actually shown that if you can't have a magic refrigerator, then you can't have a magic battery. That's what it really proved. Okay, so we've gone from Clausius to Kelvin Plonk. What remains is to prove that the other way. But it's kind of a similar kind of strategy. All right, so what I want you to do next is prove that if you had a magic refrigerator, possibly combined with other devices which are okay. So if you had a magic refrigerator and coupled it with something that's real, you could make a magic battery or magic power supply. So now, 2 is to prove that Kelvin Plonk implies Clausius, but we're not going to do that. Instead, we're going to assume, we're going to work out the contrapositive. Assume that if you had a magic refrigerator, you could design a magic battery using, real devices. Okay. Think about how you would do that. Give you a couple minutes to think about that. What's the noticeable difference between the 2 statements of the second law? One of them has 1 reservoir, one of them has 2 reservoirs, right? So effectively, you're trying to work your way towards a magic battery. So you want to start with 2 reservoirs and then effectively decouple one. So like you run in a machine, think about what happens. You run an engine in a factory floor, something like that, right? And you're running what happens to the air around it? Right? The temperature wants to go up. But what if I had a magic refrigerator? What could I use that refrigerator to do? So the engine's dumping heat into the room. What could you use the magic refrigeration unit to do? Yeah, you could just turn around and suck that yeah. You could suck the heat out of the air and put it back into whatever the hot reservoir was. So that basically the air played no role. Because the heat into the air was immediately sucked back into the hot reservoir. And so you could effectively get rid of it. There's my hint. Okay, so think about running the magic refrigerator to take a normal power cycle, take a real power cycle, and then use the refrigerator to cool off the air in the room. And then that effectively becomes a magic battery. Take a second, draw it out. Oh, you got it. Okay. So, all right. Who thinks they've got it? Raise your hand if you think you do. 1. All right. Take a second. Keep thinking about it. What about on the back? Do you guys think you have it? Alex, what about you? You don't know? Okay. Mike, think you have it? Nope. Okay. Let's go through it. So we're trying to show that this is true. So imagine I've got a normal engine. Imagine I've got a normal engine. Okay. Oh, I'm going to put it off to the side just a little bit here. And what it does is we have TH and TC, and it produces work. It takes heat from a boiler or something hot, and it dumps heat into the room, into the cold reservoir, and it produces work. This is just a normal power cycle. There's nothing wrong with that. Okay? But I want to turn this into a magic battery. And a magic battery would just take heat from the hot reservoir and dump it into work and get rid of, basically I want to get rid of the exhaust, right? That's what I want to get rid of. Do we all agree? So if I want, what I could do though is, what's the effect of that exhaust? Well, it makes the hot reservoir, dumps heat in there. But if I'm allowed to use a magic refrigerator, then I might hook the refrigerator up and just use it to reroute the heat from the air back into the boiler or the ignition chamber, whatever, okay? Into the cylinder, piston cylinder, whatever. Okay, so what I could do is, if I had a magic refrigerator, I would use it to cool off the air. So this is a magic refrigerator, okay? The opposite of Santa Clausius. Okay, so if I have a magic refrigerator, I could use it to cool off the air, and what I would have to do is make sure that the amount that I cooled it off exactly equaled the amount that of heat that I put in. And if I balance the numbers, then it's effectively the same as just doing that and eliminating this reservoir in the first place. Okay? And then I just kind of put a bigger box around the whole thing. Think of it as one giant cycle. And effectively, I've got a magic battery, or something which takes heat from this case, from a boiler, and I use it to just produce work with no waste.
Did engines back then kind of do something like that? Kind of like a secondary motor that ran off the exhaust fumes?
You can do that to boost efficiency, but not forever. Like it's not 100%. You'll never, you cannot, right? Because if you have that, it means it is mathematically the same as saying that I could take the end of just a plug and come with some sort of, novel plug where I just hold it up in the air, and then all the heat comes from the air into the plug, and I use it to power a computer or whatever. Never happened. Can't do it. All right? Okay, let's take a 5-minute break, and then we're going to do some other similar kind of math proofs. Well, again, you have to weigh the negative costs of the alternative. You can't pretend that there's no cost to carbon, hydrocarbons. You have to balance there is a potential negative for nuclear, but we also know there's a huge negative to hydrocarbons. So
But I'm just saying, like, if the government contracted a company to build a nuclear reactor, but then managed it themselves, maybe we wouldn't have this
yeah, I don't know. I mean, it's designing a system that is safe is not easy. It's not something that I know anything about. That's the nice thing about studying theoretical physics. If I screw up a minus sign, oh well. If I'm doing something that people's lives depend upon, that's even if the math is easier, the stress is much higher. Okay. All right. All right, let's do another one. So Well, it's another similar kind of one here. I'll do it on the board, so you don't have to. All right, but, so what we can do, it's the same kind of logic there. What we could do is, what I want to show is that all Carnot cycles operating between the same two reservoirs have the same efficiency. Okay, so I want to prove that all Carnot cycles have the same efficiency, which means that, remember I used the ideal gas as a crutch to do the math, but if I can prove using the second law of thermodynamics that all Carnot cycles have the same efficiency, that means that if I figured out some way to make a Carnot cycle out of, I don't know, Pez candy, then it would have the same efficiency. I mean, I don't know how I would make it, but that's a different task, all right? All right, so, so what I'm going to do is I'm going to actually start with, so I'm going to have these two cycles, and I'm going to couple them to the same reservoirs. And so what I'm going to do, I want to assume that there are two different efficiencies. Okay, so these are both power cycles. And I'm going to assume that they have different efficiencies. So what was the symbol we used for efficiency? You remember? Greek letter eta. So I'm going to say this one has efficiency eta, and this is efficiency eta prime. Just different numbers. And I'm going to assume they're different and show that if they are different, basically I can break one of the laws of thermodynamics. Sorry, break the second law. Therefore, they can't be different. Okay? And so the idea would be, so there are two power cycles, these are reversible engines. So I have Q, how do I label this here? I'm going to couple those. Well, okay. So again, I'm going to sketch this. I'm not going to run through with numbers here, but you'll get the spirit of it. You have to go through and actually put in equations, like numerical values for the heat word for the two cycles. You have hot heat prime, cold heat prime. You have work and work prime. And you have to go through and check the algebra, heat in, is the heat out, all that kind of crap. Okay, so now let's assume that the efficiency of this one is greater than the efficiency of this one. They're both reversible, but assume that this one is more efficient. Okay? So I could do that. And so what that means, let's think, what does that mean? Oh, sorry, these should be heats. This exhaust. So it should be out. Okay? What does that mean? So if you increase the efficiency, what that means is that if you have, get my numbers right. If I increase the efficiency, then that means that if you have the same amount of heat in, this one produces more work. Right? If it's more efficient, for the same input, you get more of the good stuff. Okay? So this would mean for the same heat in, we get more work from eta prime cycle. Okay? So I could do that way. me think about this for 1 second here. So what you could do is those, which means that number bigger. Yeah, okay. So let's turn it around then. What I could do is, what if these are reversible, correct? So that means I could adjust the power input and output. So what if I dialed it in so that the work produced by this one equaled, sorry, I want to reverse this one. So what I could do is reverse all the arrows here. Do these in blue so you can see that. So if I reverse all the arrows, because they are reversible, and what I actually did was I used the power cycle to power the refrigeration cycle. Just plug it in. All right, so if I balanced so that the work numbers were the same, so that the power produced by the engine powers the refrigeration, the Carnot cycle, which has been reversed into a Carnot refrigerator. Right? Because remember, for reversible cycles, I can reverse them for free. Now, if this one was less efficient as an engine, then that means that to get the same work, I would have needed to increase the heat in because it was less efficient. And after I reverse it, what that means is that there's more heat going into the hot reservoir than there is being extracted into the engine. So overall, the net effect of this is that you have heat that starts at the cold reservoir and ends in the hot reservoir. So because this one was less efficient as an engine, that means that as an engine, it means that to get the same work out, you had to put more heat into it because it was less efficient. When I reverse it, that means that you have more exhaust. And therefore, overall, you have more heat going into the hot reservoir. And overall, you have more, you have heat being extracted from the cold reservoir. And there's no other work, so that's it. So we can use, if this is true, you could reverse one to break Clausius statement. You could break the Clausius statement. So if eta is not the same as eta prime, we can break Clausius. The Clausius statement. Okay? I apologize. In my notes, I actually reversed it the other way and I used it to make a magic battery. But then it's harder to see the work and the magnitude, to see that overall it goes that way.
What you're saying is you're pulling heat out of the cold bank and the heat from the work, or the heat from the motor, and it's equally the same.
I make the work delivered by the engine equal to the work needed by the refrigerator.
So you're not adding heat to the top bank, no?
This one, well, okay, it was a power cycle. Both were engines, but they were reversible. So if I reverse one of them, it turns into a refrigerator. So it goes from absorbing heat to emitting heat. And it turns out that if I ran it as an engine, and reversing it only puts minus signs. It doesn't change the magnitudes of the numbers. So if this one was less efficient, then when I ran them with the same amount of work, if it was less efficient, it needed more inputs. So this heat as a magnitude is bigger than this heat. Okay? So that means that when I reverse this, then overall, the total heat for the whole thing is going into the hot and out of the cold. Right? These are all, the wordplay is the wording is a little tricky, right? But is the idea clear? I guess is the idea. Hopefully. So, but there's nothing special about what was eta and what was eta prime. The point is, if they're not equal, if it was less than, I would have just reversed the other one and got the same result. So the point is, I didn't tell you there was any detail. There's nothing special about this one versus that one. The key was that they weren't the same. So if they don't have the same efficiencies, I could reverse them to break the statement. I can also reverse it. I can do it a different way. I could run this heat into that. I could, instead of balancing the works, I could couple the exhaust like we did before, and then you would break Kelvin Plonk. You can do it either way. It doesn't matter.
If they're not equal, would one outpace the other, and then the two reservoirs would normalize?
Well, for right now, our reservoirs, we're taking an idealized limit where they're really big, infinitely big. So it's not about the reservoirs. But if they were finite sized, then you would have something like that. If they were finite sized, you would drive one of them to zero or something.
Well, could you have once you have where they would become the same temperature, and then you couldn't do anymore?
That will happen too. Yeah. It will turn out if they have the same temperatures, you can't extract work. That's true.
This is still imaginary, right? Not possible.
Well, these are Carnot cycles. Okay, so Carnot cycles are reversible. They can't happen.
Yeah.
But they don't break a law of physics. They just don't happen in practice. Well, all right, they just don't happen.
There's no examples of something kind of like this happening.
No.
Yes, yes.
However, but so Carnot cycles are at the threshold of what's even physically possible. In reality, you can't even get there. Right? But they don't, in principle, break any rules. They are the dividing line. If you try to do better than Carnot, it breaks the second law. If you try to do, they're the dividing line. Yeah. So here's the last little thing on that. If you, I think I won't do that one. It's kind of the same proof. Basically, you can do the same basic thing, but now make this one a Carnot cycle, and make the other one be a real engine, and then reverse the Carnot cycle. And what you can show is that if the efficiency of the real engine is better than the Carnot cycle, then it breaks the second law. I'm not going to do that one, but it really is the same logic. Okay, so not only do all Carnot cycles have the same efficiency, regardless of what they're made of, you cannot do better than them, because if you could do better than them, you could use it, you would set it, so take an engine that's more efficient than a Carnot cycle, put it next to a Carnot cycle, reverse the Carnot cycle, and you could use it to the different way you can do it, but either way, you're going to break one of the first and the second law. So therefore, come back to the statement that I made last class, where all Carnot cycles are going to have the same efficiency, and any other cycle is less efficient. Full stop. No matter, and I have not said anything about what the fluid is, how you design the engine, how many heat exchangers, how many boilers, how you insulate your pipe. None of that matters. You cannot do better than this without breaking the second law of thermodynamics. Full stop. That's just it. So no amount of tweaking or fiddling around or what, you're just never going to break these limits. It cannot be it. It's just it. That's it. Okay. All right. We don't talk. Okay. Is that okay? All right. kind of running a little behind. So I'm going to summarize some things here, kind of give a flavor for it. I don't know that the problem with summarizing is the textbook does not do a good job of deriving these things, but there are videos online of this. Wikipedia also has a good article on this. What I'm going to do is derive something called the Clausius inequality. I'm not going to derive it because I'm out of time, but I'm going to suggest how you would do it. The way that all of these results arrive is you basically take a system and you try to break the second law, one of the versions. And that's going to set a limit as to what's possible. That's really what happens here. So, okay. So, I'm just going to sketch how you would do this. Should turn it on, yeah. I'm going to sketch how I would do this, and then if you want to, you can think it through. I'm just about out of time. So imagine I've got a factory floor. You got machines everywhere, motors running, whatever, okay? So motors and refrigerators or heating, cooling, whatever, sorts of units. And what you can do is this is just a sketch. Sketch of the Clausius inequality. You really have to watch the minus signs on this. You got to really put formulas down and watch all the minus signs. Okay, so the idea with this one is going to be that you have two reversible cycles. Put one here. These will be reversibles. I call these A and B. These are reversible. And then let's put an irreversible cycle there. I don't know. Let's just put dotted lines around. This is a real cycle. Call it C. Okay, it's like a real thing. And you don't even have to have the same reservoir. So you could have A is going to talk to this one, so I can call this at some temperature T1, and then it's easiest if you, again, this is not the only way to derive this thing, but it's one way. Call that some big reservoir with temperature T0. You got another reservoir with some temperature T2, and okay, these are reversible things. They talk to this, and you can have work. If the power cycles, they produce work, whatever. And then C, it's just a machine. Who knows what it does? Maybe take some heat from here, some heat from here. It could be in general, just whatever. And dump some heat here, whatever. And then maybe it consumes or produces work itself. Okay? C is basically arbitrary. A and B are reversible. C is arbitrary. Okay? But once you start including something that's arbitrary, then the statement you derive is for anything. Right? I mean, who knows? Anything could be hidden in here. You could have the Keebler elves hidden inside there, little unicorns and glitter and whatever. Anything could be in there. All right? So anything you can state becomes very general. So what you're going to do basically is the following. If these start out as power cycles, what you're going to do is reverse them and run them as refrigerators, such that you can, and the goal is the following. The goal is that you just can disconnect these reservoirs. You're going to balance the numbers. You got to put it in as an algebraic equation. So that the heat, so you run these as refrigerators, so that the heat dumped is the heat in, and the heat dumped here is the heat dumped there, things like that. And these are refrigerators, and you have work going in, let's say this produces work, hypothetically. Okay? So if you do that, if you disconnect these reservoirs, what's the problem? What might it do?
Favor one or the other.
Well, if they're both disconnected, like you balance the heats, now you can ignore these, you're left with one giant reservoir, and you have this should be work in now, because it's a refrigerator, and then you have work out. So the problem comes, you have to make sure that what you can't have is Kelvin Plonk being broken. So you can't produce work. So what you have to make sure is that the net amount of work is negative, because you cannot produce work. You can consume work, but you can't produce work. Right? So what you're going to have to do, you got to write it all down as a series of conditions, just to make sure that when you add up all the work, it is negative.
You're saying the work coming out of C has got to be less than what we put.
I'm saying that the total, if I view this as one giant thing, the total work has to be negative. Right? Or from the first law, that's the same as saying that the total heat from the reservoir has to be negative. Right? But you cannot have it be positive, because if the work is positive, you effectively have a matching battery. So that can't happen. When you work that out, you get the following condition. We must, W net must be less than or equal to 0. It can be 0 too. It's 0 if it's reversible, it turns out. So, right. Let me put this on the other side. This is to not break the second law. To not break the second law. So when you write it all down, you get the following formula. You can relate heats to works, and what you find is that because you can relate heats to works because these are all cycles, so heat for each cycle has to equal the work for each cycle, and you get an equation. Basically, it says that when you add up the heat going into this, all the heats going into, so it'd be the heat, extracted from each reservoir, divided by the temperature. I'll write it all. You learn that the heat going into cycle A divided by the temperature of A, plus the heat going into cycle B divided by the temperature of B, plus the heat going into cycle C divided by the temperature of C, must be less than or equal to 0. Does that look sort of familiar? What was the formula we had for a Carnot cycle? For Carnot, we had Q H over QC, absolute value, equals T H over TC. I may have them upside down, but it doesn't matter. Or, putting in minus signs, we get 0 equals QH over TH plus QC over TC. Getting rid of the absolute value sign. It's the same. Well, except this is an equality because it was reversible. This is an inequality because this was non-reversible. If this becomes reversible, it becomes equal. Okay? But because this is an arbitrary thing in the middle, then this equality must hold always for any system. So we get the following result. It's called the Clausius inequality. Now I'm being kind of sketchy here, but I'm just out of time. What we find in the Clausius inequality is that in any cycle, no matter how complicated, but no matter how many moving pieces or sub-components, whatever, so any system which is in contact, so you have any sort of, monster, could be anything. And if it's in contact with reservoirs at temperature 1, temperature 2, temperature 3, temperature N, right? If it's in contact with them, maybe producing work, maybe consuming work, doesn't matter, right? Right? So the statement is, for any cycle, no matter what it's made of or any details, it must be that the sum over all heat exchanges over all reservoirs, you have that the heat exchanged with the reservoir divided by the temperature of that reservoir, that quantity must be less than or equal to 0. This is the Clausius inequality. So that's kind of a big deal, because anytime you can say something so large, right? It doesn't really, it's for anything in nature, that's a big deal. It's the Clausius inequality. In particular, what if you had an infinite number of reservoirs that, and they had kind of many different infinitely many different temperatures. And the cycle kind of talks each one infinitesimally. More or less, what do you think is going to happen to the sum? You have a whole bunch of, even an infinite number of infinitesimal heat exchanges. That's going to be a limit. You're going to get an integral. So what you can do then is if you have a continuously changing, instead of having discrete things. So for example, what this could be is you put the system in contact with boiling water, you pull them apart, let the water cool off a little bit, then you put them back in contact, let it cool off again, then again, and again. Or you could do that continuously just by sort of slowly bringing something near a boiler and slowly pulling it away. You scan through all the temperatures and heat exchange at each temperature. So you can have one reservoir by adjusting kind of how much you talk to it. It effectively is like having maybe different reservoirs. Things like that. So what we get in calculus speak is the following. So when you have continuous amounts of heat or changing amounts of heat, you can write it like that. It's the same thing. Right? Have you guys seen things like this in Calc 3? You must have. Only 2 more weeks. Only like 2 more weeks, maybe 3 weeks. Okay. Anyways. How do I describe this? Oh, I know. So how about this? So this is true. Now, if it's reversible, this becomes 0. So if everything is reversible, so I could write del Q, just to remind myself, over T, just limit ourselves to reversible. So it's always reversible. And then you add up all those little changes around a cycle, around a loop, that would equal 0. Okay? Have we ever seen, so this is some little quantity, some little bit, right? And you're adding up all these little infinitesimal things. Have we ever seen situation where you go around a cycle and you add up all the little changes, all the little bits, and you get 0? What about cycles? Begins with a P, ends in a Y. It's a property, right? This is what we would have for any property. If you have a cycle and you were to integrate the changes in pressure around a cycle, what would that be? 0. Integrate changes in internal energy around a cycle, you get 0. Right? Because when you add up all the little changes in properties, you have to get back to the same state. What we can conclude then is this thing, that there must be a property, such that you could write it like this. So
Circle on the integrand or
that
whatever.
just means integrate around a loop in the space. Closed path.
Because yeah, I mean, we've done integrals, but she hasn't done anything with a circle on the integral. But I don't know.
You've done line integrals? That's the last section. All right, we're gonna have to do a lot of catch up in electricity magnetism. Okay. All right. There must be a new property because this mimics this. So I'm just gonna give it a random letter because I'm so super and my name is Sean. I'm going to call this new quantity, I'm just assign the letter S for no particular reason. And what I will say is whatever this thing is, it's a new property, I mean a thermodynamic property. And okay, actually a new property called S, no, it's called entropy. And such that if the heat, if the cycle is reversible, or if the process is reversible, that the change in S equals the reversible heat over the temperature at which it is exchanged. Okay. Does that mean, going through the logic, does that mean that the change in entropy is always delta Q over T? No. It's only equal to that when the heat is exchanged reversibly. Entropy is always defined, but you can only calculate it using this if it's reversibly done. You have to use other stuff to find it other ways. This is what entropy is. Well, or at least it tells you how it changes. So we come to our last way to state the second law of thermodynamics, which is kind of the more quantitative one. What it says is the following. So this is going to be the entropy version of the second law. Okay. Entropy version of the second law states that there is a property called entropy. Don't get it confused with enthalpy. It's entropy. The symbol we use is S. So it's like pressure, it's like internal energy, it's like enthalpy, it's like temperature, it's like specific volume. It's another property of the system. The tricky thing about it is you can't see it. You don't have a gauge that easily measures it. But whatever, it's there. Such that ds equals the reversible heat, the temperature. Okay? And so this is, I guess, so we have that. And then the other thing we have, which is kind of an interesting thing, is that for any closed, isolated system, the entropy cannot decrease. It's like a ratchet, you know. It goes you turn it, and it tightens one way. It tightens the bolt. You reverse you pull the ratchet back. The bolt doesn't keep turning, so the bolt just goes one way. So what happens is this: you start off with a system. You know, you have a system. You put it in a box, whatever. It does whatever it's going to do. And then if you come back to it at a later date and open that box, and you ask, what's the entropy of the system? You know, even if it wasn't in a cycle, it could just be wandering around doing whatever, right? You come back at a later date, you open that box, and you ask, well, what's the entropy now? The entropy at the end will never be less than it was at the start. It could be equal, but it will never be less than. Okay? So, entropy, so sometimes people say entropy always increases. Have you heard people talk about that ever? Maybe not. Some people have. That's not quite right. The statement is it can never decrease. It could maintain. Right? That's, there's that. Wait a minute. Why is this a big deal? I mean, we said entropy is a property. You have any cycle, the entropy change is going to be what? For any, zero. Well, why is that a big deal? I mean, well, when we have thermodynamic cycles, we have heat in and heat out and work, right? That's the whole point. There's heat, work in the cycle. This is like when there's no inputs or outputs at all. So this is a little different statement than that. So that's why here's how you can show that, incidentally. For a second here, just to get my logic a little bit straight. So you take a system to be whatever you want, and yeah. So you take a system and so take a system, let's see, what's our system going to be? Does anybody have a pet? Anybody have a pet? What pet do you have, Gabe? Dog. We take Gabe's dog. What's your dog's name?
Bella. A dog named Bella.
Bella, I'm sorry. Put Bella inside the box, and we launch Bella into space. Sorry, Bella. Okay, but at the beginning, Bella was, you know, alive and happy and whatever, and then we check in 3 months later. Sorry. Okay, so here's what we're going to do. We're going to use the Clausius inequality. The Clausius inequality only applies to a cycle. Ooh, that's tricky because I have to resurrect Bella. Now, let's do something simple. Anyway, all right, we won't be so grim. Sorry, Bella survives. All right, let's, it could be water, okay? It could be liquid water, puddle. We launch it into space, we do whatever, okay? We go into space, well, what we actually imagine is that we start with liquid, and then maybe it goes into space, whatever, and we may imagine that it is isolated. So we have from state 1 to state 2, Q1, 2 is 0. It's isolated, fully, it's in a box, fully whatever. And then imagine that we reversibly bring it back to here. That's the problem. I can't use Bella because I don't know how to reversibly. But anyways, all right, bring it back to life. Okay, so you know over here maybe it's ice. Whatever. Some state, it doesn't matter. Some state here. There's no heat exchange going to there, and then it comes back to there. I guess if it becomes ice, then that's not going to happen. All right, so I go one way with no heat, and I come back with heat, and it's done reversibly. So the Clausius inequality says that if I were to look at this, I would have 0 is going to get delta Q over T around the cycle. That's the Clausius inequality. Now I write that as the integral, so I get 0 greater than or equal to the integral from 1 to 2 plus the integral from 2 back to 1. Right? I'm integrating around a closed loop, and I just break it up into a forward and a backward integral. Let's do it here. I'm almost done. But from 1 to 2, what was the heat? From 1 to 2, the heat was 0. And 2 to 3, or sorry, 2 back to 1, the heat was reversible. So what that tells me is the following. 0 is greater than or equal to this, but that's the integral of ds from 2 back to 1. So that means, and that's just going to be the change in x. Sorry, I go from 2 to 1, that's going to be S1 minus S2. Therefore, the entropy at state 2 must be greater than or equal to the entropy at state 1. So, when the system was closed and isolated, when I didn't talk to it in any way, not just me, but anyway, so fully isolated, the evolution of it is necessarily such that the final entropy is never less than the initial entropy. They could be equal, but they'll never be less than. Okay, so that's the. So what have I done there? This is kind of my way of justifying this. This is the entropy definition of the second law. And what I did is I used the Clausius statement, which came from the other two versions, to derive this same fact. So this shows that you can go from Kelvin, Plonk, and Clausius to the entropy version. I haven't gone from entropy version back to the others, but you can. I'm just running out of steam at times. Okay? That's the second law of thermodynamics. The first two are very wordy. This is the one that's going to give you numbers out. Okay? what we're gonna do next class is we're gonna go over to the MTI building and look at the refrigeration cycles. And we'll look at what they've got. And we'll talk about the stages of it. And I probably am gonna ask that you guys take a picture or maybe I'll take a picture and then so you guys can remember, because then we're really gonna talk about cycles after Thanksgiving here. We're gonna go through the parts of it after Thanksgiving, but tomorrow's the day we're gonna look at it, okay? So, and this stuff's gonna come up. It turns out then, when we have any device, we wanna talk about like, what's the best turbine, or what's the, anyways, when we wanna compare like how good or bad is a turbine, what you're gonna do is compare the work done in reality to the work you would have got if entropy stayed the same. It won't go down, but you'll use zero change in entropy as your benchmark to compare what's the ideal turbine. And then so what we will do is come up with efficiencies for, a nozzle, a diffuser, we'll have a boiler, that'll have entropy change. But whatever, we'll have different components and we will have different efficiencies for each one, defined by comparing the real thing to what it would look like if there was no change in entropy. And you'll go through and use that to analyze how good is your refrigerator or your air conditioning unit or your power plant or whatever. Right, so that's the idea. Okay, stop there.